Welcome back to the channel. If you are currently architecting a solution in Azure or really any cloud environment, you are immediately hit with a fundamental, inescapable question: where do I put the data? It sounds like a simple question, but in the Azure ecosystem, storage is not a monolith. It is a complex matrix of specialized services. You have blob storage, data lake storage Gen 2, Azure Files, and Azure Managed Disks. Now, I see this happen constantly in architecture reviews. Engineers treat these services as interchangeable buckets. They think, storage is storage, I'll just pick the cheapest one. If you pick the wrong one, three things are going to happen. First, your application performance is going to bottleneck in ways you didn't anticipate. Second, your management overhead is going to skyrocket because you're fighting against the service's native behavior. And third, and this is the one that gets people fired, you get a bill at the end of the month that is 10 times higher than you estimated because you fundamentally misunderstood how transaction costs work versus capacity costs. Today, we are not reading the marketing brochures. We are going deep. We are going to tear apart the architecture of these four services. We will look at how they handle data at the byte level, we will compare their protocol support, and we will break down the specific pricing models that catch even senior engineers off guard. By the end of this video, you won't just know what these services are, you will know exactly which one fits your specific architectural constraints. Let's get into it. Let's start with the absolute foundation of the Azure cloud, Azure Blob Storage. If you understand blob storage, you understand the bedrock of Azure data. Technically, this is a massive, scalable object store. It is critical to distinguish this from the file system on your laptop. A file system manages data as a hierarchy of files and folders. An object store manages data as flat objects. Each object includes the data itself, a variable amount of user-defined metadata, and a globally unique identifier. When we talk about blob, we are actually talking about three distinct types of blobs. Understanding the difference is critical for your application logic because you cannot simply convert one to the other on the fly. First, you have block blobs. This is what 90% of you will use. These are optimized for streaming and storing cloud objects like documents, videos, pictures, backups, and logs. They are composed of individual blocks, each identified by a block ID. The magic here is parallelism. You can upload blocks in parallel to massive increased throughput and then commit them together to form the final object. A single block blob can store up to roughly 4 gigabytes. 75 terabytes of data. Second, we have append blobs. These are specialized for append operations. Think about logging. If you have a distributed system with 1,000 containers writing logs to a central storage, you don't want to lock a file, read it, modify it, and write it back. Append blobs allow you to simply add a block of data to the end of the blob immediately. It is optimized for high-volume write operations where data is rarely modified once written. Third, page blobs. These store random access files up to 8 terabytes in size. These are optimized for frequent read-write operations on specific byte ranges. Technically, these are the underlying storage infrastructure for Azure Virtual Machine disks, but we will get to disks as a separate service later. Now, let's talk about the architecture. Blob storage uses a flat namespace. This is the most important technical distinction you need to memorize. In a flat namespace, there are no real folders. None. You might see a file path that looks like folder1/folder2/file.txt, but Azure doesn't see directories. It sees a single object inside a container with a very long name that just happens to have forward slashes in it. The slashes are part of the string, not a structural element. Why does this matter? It matters for performance. Imagine you have a virtual directory named Folder1 that contains 10 million files. You decide to rename Folder1 to Archive. In a real file system, that is one operation. In a flat namespace, Azure has to perform 10 million individual rename operations. It has to copy every single object to the new name and delete the old one. This consumes massive amounts of compute, takes a long time, and costs you money for every single write operation. However, where blob storage shines is its access tiers. You must master these to control costs. 1. Hot tier. This has the highest storage cost but the lowest access cost. You use this for data that is actively being read and written. 2. Cool tier. This offers lower storage costs but higher access costs. This is for data stored for at least 30 days. If you delete it before 30 days, you pay an early deletion fee. 3. Cold tier. Even cheaper storage but higher access costs. This is for data stored for 90 days. 4. Archive tier. This is the cheapest storage on Azure. We are talking pennies per terabyte. Effectively, this is tape storage in the background. But the data is offline. You cannot read it instantly. To read it, you must rehydrate it, a process that can take up to 15 hours depending on the priority you pay for. The transition between these tiers shouldn't be manual. You should use lifecycle management policies. These allow you to write JSON-based rules that say, if this file hasn't been modified in 30 days, move it to cool. If not accessed in 180 days, move it to archive. This automation is the key to cloud cost optimization. Now, let's look at the evolution. Azure Data Lake Storage Gen 2, or ADLS Gen 2. A few years ago, Azure had blob storage and a separate, expensive service called Data Lake Gen 1. Gen 1 was great for analytics, but incompatible with the vast ecosystem of tools built for blob storage. Gen 2 is the convergence. It is built on top of Azure Blob Storage. It is not a separate physical infrastructure. Technically, it is simply a feature flag enabled on a standard storage account. So, what makes it a data lake? It comes down to two things: the ABFS driver and the hierarchical namespace. First, the ABFS, Azure Blob File System. This allows the storage to interface natively with Hadoop-compatible ecosystems. If you are running Azure Synapse, Azure Databricks, or HD Insight, you are using the ABFS driver. It is explicitly optimized for high-throughput analytical workloads where you are scanning massive datasets. Second, and most importantly, the hierarchical namespace. Remember how I said blob storage is flat? When you enable HNS, you turn that flat namespace into a real structural file system. You get actual directories and subdirectories. Let's go back to that rename example. In ADLS Gen 2, if you want to rename a folder containing 10 million files, it is a single atomic metadata operation. It updates the parent directory reference and boom, it's done in milliseconds. This atomic manipulation is mandatory for big data analytics engines like Spark or Hive. These engines frequently write data to temporary directories during job execution and then rename them to the final output directory at the end. On standard blob storage, that rename could take hours. On Gen 2, it's instant. Furthermore, because it's a real file system, ADLS Gen 2 supports POSIX-compliant access control lists. In standard blob storage, you usually control access at the container level. It's all or nothing. In Gen 2, you can set read, write, and execute permissions on specific nested folders for specific Azure Active Directory identities, just like you would on a Linux server. So, the rule of thumb: if you are building a data warehouse, a lakehouse, or doing heavy analytics, you enable the hierarchical namespace. If you are just serving images for a website or storing backups, you stick with standard blob storage because HNS adds a slight cost overhead for the metadata management. Next up, Azure Files. While Blob and Data Lake are cloud-native concepts designed for modern applications, Azure Files is the bridge to the legacy world. It provides fully managed file shares in the cloud that are accessible via the industry-standard SMB, Server Message Block Protocol, or the NFS, Network File System Protocol. The architecture here is designed to replace your on-premises NAS, Network Attached Storage, or file server. You don't want to manage a Windows Server VM just to share files, you use Azure Files. Let's break down the protocols because they dictate the architecture. SMB shares are what you use for Windows and general-purpose file sharing.
You can mount an Azure file share on a Windows, Linux, or Mac OS machine anywhere in the world, provided port 445 is open. A critical feature here is identity integration. You can integrate Azure files with your on-premises Active Directory Domain Services, ADDS. This is huge. It means you can migrate a file server to Azure, keep all your existing ACLs and NTFS permissions, and your users can access the shares using their existing corporate credentials. No new keys, no SaaS tokens, just standard Windows authentication. NFS shares. These are strictly for Linux workloads. NFS 4.1 support in Azure files is designed for things like SAP application layers or container storage. Important note, NFS shares only work within the Azure Virtual Network. You cannot mount an NFS share over the public internet due to security constraints. You need a VPN or ExpressRoute. Now we need to talk about performance tiers in Azure files because the architecture changes completely and so does the billing. Standard Azure files runs on hard disk drives, HDD.
It uses a pay-as-you-go model where you pay for the storage used and the transactions performed. This is great for general file shares. Premium Azure Files runs on solid-state drives, SSD. The billing model here changes to provisioned. You pay for a set amount of storage and IOPS regardless of whether you use them. This tier offers extremely low latency and high throughput. Here is the trap. If you have a chatty application that does millions of small reads and writes, standard files might actually be more expensive than premium because of the transaction costs. Conversely, if you provision a 10 terabyte premium share but only store 100 gigabytes, you are burning money. There is also a superpower feature for Azure Files called Azure File Sync. This allows you to install an agent on your on-premises Windows server and cache your Azure file share locally. Your users access the local server at LAN speeds, but the data is tiered up to the cloud. It effectively turns your small on-prem server into an infinite tiered file server. Finally, we have the heavy lifter, Azure Managed Disks. While Blob, Data Lake, and Files are accessible via network endpoints, REST APIs, SMB, NFS, managed disks are block storage devices designed to be attached directly to a single virtual machine. They act as the physical hard drive for that server. Under the hood, these are actually .vhd files stored as page blobs in Azure Storage, but Microsoft abstracts all that complexity away, hence managed disks. You don't manage the storage account, you just provision the disk. The deep technical differentiation here lies in the tiers and the SLA. 1. Standard HDD, magnetic spinning platters. Good for dev/test or non-critical backups. Latency is variable. 2. Standard SSD, entry-level solid state. Better consistency than HDD, but IOPS are still relatively low. 3. Premium SSD, V1 and V2. This is the production standard. It delivers high throughput and low latency. In V1, performance is tied to size. Larger disks get more IOPS. However, Premium SSD V2 is a game changer. It allows you to provision capacity, IOPS, and throughput independently. This is massive for databases where you might need high IOPS but low capacity. 4. Ultra Disk, the highest performance, sub-millisecond latency. You can dynamically adjust the IOPS and throughput of the disk while the VM is running. This is for your mission-critical SAP HANA or top-tier SQL workloads. A unique feature to mention is shared disks. Historically, a disk could only attach to one VM, read-write once. Azure Shared Disks allows you to attach a managed disk to multiple VMs simultaneously, read-write many at the block level. Why? To support clustering applications like SQL Server Failover Cluster Instances, FCI, or legacy clustering protocols that require a shared block device. We've covered the architecture. Now, let's compare them head-to-head across three vectors: access method, performance, and cost. 1. Access method. Blob and ADLS Gen 2, accessed via REST APIs. This is for cloud-native apps. You don't mount these to an OS in the traditional sense. Even though tools like Fuse adapters exist, they are not native block devices and shouldn't be treated as such. Azure Files. accessed via SMB/NFS. It looks like a folder on your computer. It is a network share. Azure Disks, accessed as a physical device by the OS. It looks like a C drive or /dev SDC. 2. Throughput is king. These services are designed to stream gigabits of data per second. Latency is decent, milliseconds, but they are not designed for random read/write operations on small blocks of data. Azure Files. Premium Files offers single-digit millisecond latency. Standard Files has higher latency. Throughput is generally lower than blob storage, but sufficient for file sharing. Azure Disks. IOPS and latency are king. UltraDisk and Premium SSD offer sub-millisecond latency. This is the only choice for running a database engine or an operating system. 3. The pricing trap. Here is where you lose money. Blob/ADLS. You pay for capacity, which is cheap, but you pay for transactions. If you write an application that polls a blob every second to check for changes, you will generate millions of read transactions and get a massive bill. Azure Files. Standard. Pay for used capacity plus transactions. Premium. Pay for provisioned capacity. If you provision 10 TB and store 1 GB, you pay for 10 TB. However, transactions are included. High churn workloads are often cheaper on Premium because you aren't nickel and dimed on the operations. Azure Disks. You pay for the provision size. If you buy a 1 TB Premium SSD, you pay for 1 TB every month, even if it's empty. You are paying for the reservation of that physical hardware. Let's cement this with 4 quick scenarios to help you visualize the decision process. Scenario A. The Netflix competitor. You are building a video streaming service. You need to store petabytes of MP4 files and stream them to users globally. Choice: Azure Blob Storage. You need the cheapest capacity, cool/cold tier, global redundancy, GeoZone redundant storage, and high-throughput streaming via CDN integration. You don't need a file system. You need an object store that can serve content via HTTP. Scenario B. The Data Science Platform. You are ingesting raw sensor data, cleaning it using Databricks, and querying it with Synapse. Choice: Data Lake Storage Gen 2. Why? You need the HNS, hierarchical namespace, for atomic directory operations so your Spark jobs don't hang while renaming folders. You need granular ACLs to secure specific datasets for different research teams. Standard blob storage would choke on the metadata operations. Scenario C. The Lift and Shift Legacy App. You have a legacy CMS, content management system, running on Linux that writes config files to a shared directory. You are moving the VMs to Azure but don't want to rewrite the code. Choice: Azure Files, NFS or SMB. Why? The application expects a file system path. It doesn't know how to speak REST API. You mount the Azure file share and the app works without code changes. If you tried to use blob storage here, you would have to rewrite the application's I/O layer. Scenario D. The SQL cluster. You are running a high-performance SQL Server cluster on virtual machines. Choice: Azure Premium SSD V2 or UltraDisks. Why? You need raw block-level access. You need the lowest possible latency for transaction logs. You cannot run a performant database on blob or files. The latency would kill your transaction times. To summarize the decision matrix, do you need to boot an OS or run a high-performance database? Azure Managed Disks. Do you need to share files between legacy servers or office workers via SMB/NFS? Azure Files. Do you need to run big data analytics with atomic directory operations and Hadoop compatibility? Data Lake Gen 2. Do you need to store unstructured data, backups, or media for a cloud-native app? Azure Blob Storage. Storage in the cloud is not just a bucket, it is a strategic architectural decision. The difference between a flat namespace and a hierarchical one, or between provisioned billing and transaction billing, dictates the performance and profitability of your application. I hope this deep dive helped clear up the confusion. If you want me to do a dedicated video on configuring the networking security for these services, specifically private endpoints versus service endpoints, drop a comment below. Don't forget to subscribe for more deep technical breakdowns. Thanks for watching and happy architecting!